right, here's a favorite topic of mine called the limiting reactant problem. What's that about? Let's use an analogy we can all relate to, and that's food. Anybody not like food? Good. If you had 6 pieces of bread and 4 pieces of ham, how many sandwiches could you make? I heard the right answer of 3. Now, sandwiches, unlike molecules and chemicals, there's no set way to make a sandwich, as Dagwood here just told us. So what we need is a balanced chemical equation. So I'm gonna be artistic and hi, Liberty. All right, so I tried to draw this piece of ham nice and thick. So this is a chemical equation, and it says 2 breads, 1 ham, 1 sandwich. So far, so good. All right, so now I'm gonna use like the mole ratio, and I'm gonna start out with 6 pieces of bread. I'm gonna multiply this by something that says 2 pieces of bread for every 1. And notice the units cancel like they should. What am I left with? 3 sandwiches. And your piece of ham got a whole lot skinny.
Yeah.
All right, and now I'm gonna turn around, I'm gonna say, okay, I got 4 pieces of ham. And now notice my mole ratio is a little different. I got 1 sandwich. I'm gonna go back to a thick piece of ham for you. So 6 pieces of bread, I can make 3 sandwiches, and then what happens? I run out of bread. In theory, I have enough ham to make 4 sandwiches. However, like Ethan said, I would just put the 4 pieces of ham in 1 sandwich. So what is the limiting reactant? Yeah, the bread limits the amount of sandwiches. So what did I do here? I calculated the amount of product based on each reactant. And in essence, that's the limiting reactant problem, is when you have 2 reactants, how much product can you make? You know, sandwiches, normally, 2 pieces of bread to 1 piece of cold cut, perhaps. And when I asked this question, immediately people were giving me the 3 sandwiches. You did it in your mind super fast, and that's because this might be a common experience. It's common knowledge that a sandwich usually has 2 pieces of bread, unless it's an open-faced sandwich. Here's a favorite reaction of chemists. To relate it to last chapter, I'll start out like this and say, what type of reaction does this look like, and can we complete it? Combustion, double displacement, single replacement. You see this single element, and so I'm gonna write the other product here because that's how I like to write these things. So this reaction is called thermite, and it's how people sometimes weld railroad tracks together out in the field. Releases lots of heat, and you get some molten iron. Now, are we balanced? I think I need a 2 here and a 2 there. So let's ask this question. Suppose I start out with 50 grams of aluminum and 100 grams of this. How much iron can I make? I'll just give myself a few more digits to work with. And what is the limiting reactant? Well, I might have to go to the periodic table and get some numbers. Hopefully that's right. I'm gonna check that one out. Are all my formula weights? I'm gonna go 2 times 55.85. Somewhere 3 times 16 ought to be pretty good. Yeah, that looks close enough. So unlike the sandwiches, you're like, oh, this is Greek, I have no clue. Well, we want to do the same process. It's the most straightforward. There's other methods we'll get to. I'm going to calculate the mass of iron based on the mass of this starting material. Then I'm going to do it again and go based on the mass of that starting material and see what happens. So I'll start out 50 grams of aluminum. Pull out your mole mount and say, Eric, you got to convert to what first? Yeah, everything proceeds through the mole. 1 mole of aluminum contains so many grams of aluminum. Look up at the periodic table. Now that I know moles of aluminum, how do I get over here to moles of iron? I use the mole ratio that comes from the coefficients in the balanced chemical equation. 2 moles of aluminum will produce 2 moles of iron. How do I go from moles of iron to mass of iron in grams? Don't pull out that number with the exponent. We're going to use this number off the periodic table. And then maybe before you pull out your calculator, you say, all right, grams, aluminum went away, moles of aluminum went away, moles of iron went away. Everything looks pretty good. So I pull out my calculator, 103.5 grams of iron. Think I can make that much? Don't know at this point. It might be like 4 sandwiches. Hey, could we name this? Iron 3 oxide. 1 mole of Fe2O3 should weigh 159. And the second half of each conversion is about the same there with the mass of iron. So then I pull out my calculator and I get something like 69.9 grams iron. So what reactant is there in excess? I got more than what I need. I make my 3 sandwiches and I have this leftover piece of ham and I stick it in my sandwich and not my wife and daughter's sandwich. Actually, I put it in my daughter's sandwich because she's growing and I sacrifice for the team. All right, so the reactant that gives you the smaller amount is the limiting reactant. So what other interesting questions can we ask about this question? How much aluminum's left over? The 6 pieces of bread, 4 pieces of ham, I had 1 piece of ham left over. How many grams of aluminum are left over? Once I know that this is the limiting reactant, I can start out with that. Convert mass into moles. I still have a mole ratio here. 1 mole of this. Ferric oxide needs 2 moles of aluminum. 1 mole of aluminum is the same thing as 26.98 grams of aluminum. We could say is consumed, is used up. And then now I can see how much aluminum is left over. So I told you the easiest thing to do is just calculate the amount of product based on each reactant. And that's just one way, and we did that. And a lot of times that works for the next question that your chemistry teacher might ask you is how much excess reactant is left over. We could also maybe look at it this way. Maybe is there any economist here? Any econ majors? Economists talk about supply and demand. When the supply is greater than the demand, you're dealing with the excess reactant. We're saying it's the excess reactant. Right. Yeah, but atoms and molecules follow their own rules, and that's the rules of definite composition, definite proportions, and atoms cannot be split nor destroyed, so they come together in certain ways. Now let's just, for fun, let's start with the aluminum and see how much ferric oxide is needed. And let's just do that because there's nothing more fun than doing mole problems. 50 grams of aluminum, 1 mole of aluminum. All right, so here we can look at this and maybe say something like, we have 100 grams of our ferric oxide, and we're gonna call this supply, and the demand, now we can call this the limiting. Any questions? I imagine the biggest question is, you still might be struggling with turning mass into moles and then into moles of something else and back into, but that is the limiting reactant problem that chemists face all the time. Any questions? Calculate the amount of product based on each reactant. Unless you're an economics nerd and you really like that language. So we're just gonna recap what we went over. More pancakes, limiting reactant, theoretical yields and percent yields. What we did with that last problem and with the bread is we calculated a theoretical yield. With 6 pieces of bread, in theory, how many sandwiches can you make? 3. With 4 pieces of ham, how many sandwiches can you make? 4. So that's what a theoretical yield is. And we'll talk about a percent yield in a little bit. So I feel inclined to tell you what I ate for breakfast. That'd just be wasting time. A fruit salad with honeydew from Guatemala that wasn't too expensive, and strawberries from California, which are in season, and then a leftover waffle with peanut butter and applesauce my wife canned last fall ago. All right, so here's a recipe. How many of you make pancakes from scratch? All right, I don't know if this looks a little heavy on the eggs for the amount of flour, but I don't think it matters. So 1 cup of flour, 2 eggs, a half a teaspoon of baking powder makes 5 pancakes. So this is like a balanced chemical equation. And I go to my pantry and I find 3 cups of flour. I open up my fridge and I say, I am wealthy, I got 10 eggs. Little joke for the times maybe. And 4 teaspoons of baking powder. How many pancakes can we make? So these are all theoretical yields. My 3 cups of flour, I look up here, and here's a mole ratio from a balanced chemical equation, just like my sandwich analogy. And I see with 3 cups of flour, I could make 15 pancakes. I don't think I could feed everybody in this room. 10 eggs, 2 eggs give me 5 pancakes, 2 eggs, 5 pancakes. I could feed everybody in this room. One measly pancake. Hopefully I'd have lots of toppings. But I find 4 teaspoons of baking powder. I can make 40 pancakes. So these are all theoretical yields based on each reactant. Now, who paid attention? What is the limiting reactant? I mean, up here. Is it flour, eggs, or baking powder? Yeah, it's flour. Gave us the lesser amount. All right, the limiting reactant is the flour. You got that perfectly. If this were a chemical reaction, the flour would be the limiting reactant. 15 pancakes would be the theoretical yield. I can't make 40 pancakes. I'd run out of it. I could try. When we got 69.9 grams of iron, that told us the Fe2O3 was the limiting reactant because it gave us the lesser amount. Yeah, and the 103.5 grams of iron, that was a theoretical yield. The 69.9 was a theoretical yield. So we go into the kitchen, put in our apron, turn the thing up on high like a good bachelor because you want to get done quick. Pull out your phone. We burn 3 of them, and a good bachelor just eats them anyway. We throw those out. 1 falls on the floor. So even though we had enough for 15 pancakes, we finished with only 11. What do we call our 11 pancakes? We call that our actual yield. That's actually what we got. Our theoretical, in theory, we should have been able to make 15 pancakes. So the amount of product actually produced in a chemical reaction, that's our actual yield. What is the percent yield? It's actual divided by theoretical. And then that comes out point something, 0.73, multiply it by 100 so we get a nice whole number, and the percent means per 100. So we only got a 73% yield, and we lose our job at Village Inn. Any questions on percent yield? Actual yields and percent yields. The actual yield of a chemical reaction, you just got to do the reaction and get it. That means it's determined experimentally and can depend on the reaction conditions. Like in the pancake analogy, I had the stove turned up too high and I didn't pay attention at the beginning. The actual yield is almost always less than 100%. So here it says some of the product does not form. Let me put a plug in for general college chemistry. You take Chem 2, we talk about equilibrium. Some reactions don't go all the way to completion. Production is lost in the process of recovering it. A mechanical loss. Let me just talk about one. I used to help my mom with her mechanical loss when I was a small kid. How many of you like to lick the beaters? Like a mixing bowl, frosting, and your mom lets you. So that's a mechanical loss, like you make frosting or cookie dough. You can't get it all out of the mixing bowl or out of the beaters. That's a mechanical loss. So these things limit the actual amount. This is perfect. To summarize, the limiting reactant or limiting reagent is the reactant that is completely consumed in a chemical reaction. It gets all used up and something is left over. So we'll be talking about a word called stoichiometry. That's what this whole business is, with coefficients in front of the balanced chemical equations. In a balanced chemical equation, what that tells us, so sometimes there might be reasons why you want the exact stoichiometric amount. You want 3 pieces of ham and 6 pieces of bread, and you don't want any excess of any chemical reactant. Theoretical yield, we've done a number of those today. We did 2 at the beginning to figure out which was the limiting reactant with the thermite reactant, 2 masses of iron, and then the actual yield, what you actually get. So talked about a mechanical loss, an equilibrium loss. Of course, the cooking, it was easy. Something gets burned or dropped on the floor. The one that gets dropped on your floor, that's why you own a dog, comes by and eats it. Percent yield, what is that? That's the actual yield divided by the theoretical yield. All right, we got a couple minutes. Got to give you your money's worth. Here is titanium chloride. If you were going to name this, what would you name it? Just straight up titanium chloride, or would it have parentheses? I'm seeing titanium in that D block there, same period of potassium. I think I got to denote the charge. I think this would be titanium 4 chloride. All right, well, we don't have to look up any formula weights. This says 2 titaniums give me 2, and 2 chlorides to give me 2 chlorine gases, diatomic element there, give 1 TiCl4. So from these coefficients, I get these 2 mole ratios. So I'm probably going to multiply this by one of these ratios and one of this by the other ratio. So when we calculate a theoretical yield, we don't necessarily have to go all the way to grams to figure out the limiting reactant. So here's my 1.8 moles of titanium. 1 mole of that to every 1 mole of titanium, I'm getting 1.8 moles. Here, 3.2 moles of chlorine gas. And I see that I need 2 of those for every 1 of those. And I get this 1.6. And I look at that, and that is the lesser amount. The lesser amount tells me this is the limiting reactant.